Hey, g'day, it's Crusader and welcome back to the Crusader model aircraft engine build. Now this is episode 9 and today I'm going to try to make the piston for the engine. And I've got some very special material, special in regard to where it came from, and we'll have a look at that on the bench shortly. Now there is a playlist for the Crusader 60 engine build and the link is up above there now, so please go back and check out any previous episodes if you haven't seen them. Right, let's have a look at this material on the bench now and then we'll get started. Now this is the stock that we're using to make the piston for the Crusader 60 engine. Now this is cast iron, it's around about 27 millimeters in diameter, and the interesting thing is that this came from a museum in California in the USA. Now, the museum is called the Miniature Engineering Craftsmanship Museum, and they have exhibits from the best model engineers from all over the world. And a contact of mine, Roger Taylor, lives in California, and he sent me the kit of parts to make the Titan 60 engine, which is now in that same museum. And he recently asked me if I had enough stock to make this Crusader engine, and I did mention I didn't have enough cast iron for the piston. And he very kindly went along to the museum and spoke to one of the in-house machinists that works there, and they donated this stock to the project. So I'm very grateful for that, and it saves me having to buy that myself. So the piston that we need to make is a bit like this one here. Now this was actually a mock-up I made for the Titan 60 engine, just to get my head around some of the machining processes. It's made of aluminium, but the finished piston was made of cast iron. So it has this baffle on top, and the purpose of the baffle is it segregates the burnt fuel from the incoming fresh fuel and air mixture. So they don't mix quite as thoroughly as they would if you didn't have the baffle. And the underside of the piston has that long slot, and that's where the connecting rod is able to pivot backwards and forwards. And other than that, it's very similar. The other difference is that it has a large port in one side of the piston, I think on this side here. And that just allows fuel and air mixture to travel up to the combustion space on top of the piston. So we're going to head over to the lathe now and we'll see how we get on. Hopefully I get the first one coming out perfectly, but you never know, that's why I've got plenty of stock. So I'm going to machine all of the features that appear on the bottom of the piston from this end. So I'm going to face it, turn it oversize, and then bore and counter bore for the bottom of the piston. And yeah, we'll leave a bit of stock on here which can be removed after we do the normalizing on the piston. So in the build notes it says to heat this up to red hot, hold at that temperature for a while, allow it to cool down slowly, and that will relieve any stresses in the piston before you finish the outer diameter. Okay, we're at 24.31 and we need to finish at just over 23.95. So I might actually leave it there. After we've done the normalizing on the piston, I'm going to pressure turn this on a mandrel just to finish off the outside, and then we'll probably also lap that very lightly. So I'm just setting my tailstock DRI now so that I can drill this hole accurately to depth, and I'm going to finish up with a 1/2 inch center cutting end mill. is we need to have a flat bore, flat bottom on that bore. Okay, so I've zeroed out the tip of the drill. The tip of the drill is now level with the end of the stock here. So we need to drill to 20.66, or just under that, probably 20.6. Now I think what I'll do next is put the big counter bore in the bottom of the piston. So it's got to be 21.34 diameter and 1/4 inch or 6.35 deep, and that will mean that I have less stock to remove with that end mill. Okay, let's do a spring pass, and we're really close, so this last cut will be very light. Okay, I'm going to put the end mill in there now and finish off the bottom of that drilled hole into a flat end. Okay, that's better. Got a nice flat bottom on the end of that hole there now. So the next step is we've got to lighten the area at the top of the piston. I've got a special tool for that, so I'll get set up and I'll show you. You can see in the CAD model how the top, that 1/2 inch bore that we've already put in the piston, is enlarged, and that lightens the piston. But in order to do that, you've got to get a specially ground boring bar inside that 1/2 inch bore, right up against the end of that bore, and then enlarge that space. Now this is the boring bar that I'll be using to do that. Now this is specially ground to fit into the bore of the piston we've already got there, and the width of that cutting edge there is exactly right for the geometry of the piston. This was sent to me by Roger Taylor in the United States, and he used this one to make the piston for his engine, so it saves me a bit of trouble having to grind up a new one. And I thought I was being really clever here. I thought I'd invert that cutting tool in the tool holder and have the cutting edge facing downwards, and then run the tool outwards from the back of the piston. And my reasoning for doing that was that I thought I'd be able to see inside to just check on the progress of the cut, but as it turns out you can't. Even if I get my head down right on the bed of the lathe and look inside, it's really hard to see what you're doing. So what I've done is I've set my DRO in the Z direction so I know exactly how deep to go. And then I just ran this over by hand and ran the tool out until it made contact with the wall of that 1/2 inch bore, and I zeroed out the other axis on the DRO. Now I've got to go a total of 4.32 millimeters in that direction, and because I got my DRO to read diameter, I've got to double that, so I've got to go 8.64 on the DRO, and we're just going to take it nice and slow and just hope for the best. So that's my zero position there. The tip of the tool would be touching the back edge of the piston skirt there now. So we're going in our total depth of 20.66. Which is just there. I just feel it touching the underside of the crown. And I've already zeroed out the other axis. So if I wind this in a little bit, I can hear that cutting now. Alright, so let's do it for real and see what happens. it's making chips, and according to the DRO that was a 1mm deep cut. I'm just going to get my head in there and have a closer look. Yeah, alright, I think that's working, so let's keep going. Okay, just stopped again. I think there's a sharp edge here which is rubbing on the 1/2 inch diameter bore we've already made. So I'm going to do a bit of regrinding on this tool and just try and relieve it. I could feel it slowing down in the cut, and just didn't want to go any further. And I don't want to open up that 1/2 inch bore more than I need to. I've reshaped that tool a fair bit. I've taken a lot of stock at the top of the shank here and just put it back in, and it seems to be working okay now. But it's a very wide cutting edge for a very narrow shank on that tool there, so you can't take heavy cuts. I'm at 1.5mm now, and we've still got a fair way to go, not even halfway. So just continue on and just take it very slowly. Okay, that's about halfway, but I can see it's rubbing again. So I don't know where. It's really hard to tell. I'm going to take the tool out and try and regrind a bit more. I did actually put some layout fluid inside that bore there, so if that layout fluid is rubbed off, you know that something's not right. Alright, I've been struggling with this for about the last 3 or 4 hours. And I cannot get this boring bar to do the undercut without rubbing on the 1/2 inch bore that's inside the piston there now. And I kept hearing it rubbing, it wouldn't cut anymore, and I take it out and regrind it, sort of try to create some clearance. And in desperation I coated this with layout fluid and then ran it again, and there's a little bright patch just there, so that's where it was rubbing. And I thought if I keep grinding that away, I'm going to have no strength left in the neck of that tool. So I decided to cut my losses with this one, and I found this tool. Now this is one that I made when I did the Titan 60 engine. This was actually turned on the lathe, and I created the profile of this using my CAD software, so I knew it would fit. What it meant was that after I'd turned it all, I had to grind the flat on the top to form the cutting edge, and then harden and temper that stock there. And I had to modify it slightly to fit inside this piston because it's a slightly different geometry to the Titan 60 engine. But I went ahead and I've cleaned out the area underneath the crown of the piston. It's not quite to the full diameter that it needs to be, but I think it's going to be okay. But in the process of messing around with this one, I've sort of ruined the bore, that 1/2 inch bore. It's sort of all rubbed and probably oversized now. So what I'll do here is I'll part this one off and keep this as a test part, so when we do the rest of the features I can practice on this one. I've got enough stock to be able to cut another piston at the other end of this piece. I'll do that off camera, and then we'll come back and we'll carry on with the rest of the features. Okay, I've caught up to where I was yesterday. So this is the second piston, and I've just undercut the crown of the piston. Now I didn't quite get to the dimension that I wanted. I'm about 1/2 millimeter short, but I think it's going to be okay. It's just trying to get the geometry of this boring bar right is really difficult because you can't see what you're doing. But all we need to do now is chamfer the inside edge of the bottom of the piston, and then I'll part this off, and then we can go ahead with the rest of the milling operations, which is to drill for the gudgeon pin, machine the baffle, and there's got to be a slot cut on the underside of the piston. So I'll get this cut off and then we'll go over to the mill. Almost forgot to do that chamfer. I'll do it now. Now, I went through yesterday and I did all of the operations on this piston here. This is the one that I messed up on the inside there, so the bore got all scratched up and scored. As it turns out, it's probably fine, but we'll go ahead now, we'll do all of the same operations on this one. This is the second one that I did, and having done this one here, I've sort of worked out better ways of holding this part. The last operation, which was to cut the baffle in the top of the piston, the setup that I used was a bit sketchy and I thought I could do better. So you'll see this little fixture make an appearance shortly, and this is going to allow me to hold the piston and align the rod, which will eventually form the gudgeon pin. So once the part goes in there, it'll automatically align, and we can do all of the features that happen after we drilled this hole for the gudgeon pin. So that's the first operation, and that becomes a reference for everything after that. So there's the slot in the underside of the piston, there's the baffle on top, and there's a large port in the side of the piston. Now, I need to tell you, don't be an early adopter. I keep finding little errors and things that I've missed in these drawings. So when I checked this drawing against the original build notes, I'd realised that I'd put the baffle on the wrong side of the piston. So I've moved it over and I've corrected the drawings. I put them on Dropbox. So if you haven't got to this step yet, get the new version of the drawings. I think it's up to like version 7 or something like that. And it will have a few extra dimensions on there as well, which sort of helps with the positioning of all those features. Okay, so I'm going to go ahead now and we're going to drill the hole and ream it, and then we'll move on from there. So there'll be no talking, I'll just do it all. I'll put some captions in, and then we'll see if we can get this to fit. Okay, that's nearly all of the machining done on the piston. What I need to do now is do the stress relieving on this part. So I have to do a bit of heat treatment and then we can finish the outside diameter. And I think that part is done. And we can fit the gudgeon pin, but that's a fairly straightforward part. That's just made from this 1/4" drill rod. It just needs to be drilled and countersunk at either end and a small aluminium cap put in either end of that pin. I'll probably do all of that off camera and then we can give this a try in the engine and just see whether we get any compression. Now that we've finished machining the piston, the next step is to heat treat this. So we're going to try to stress relieve the cast iron. The process is called normalizing, and it involves heating this up to red heat, holding it there for about 10 minutes and then allowing it to cool down very slowly. So I built a bit of a fibric hearth here. I put a piece of cold rolled steel inside the bore where the gudgeon pin goes, just to try and protect that from oxide. And I'm going to heat these bricks up first and get them incandescent. Then I'll put the part in there, bring that up to temperature and hold it, and then the heat from the firebricks will continue to keep this warm as it cools down. Ideally you would do this in some sort of a heat treat oven, but I don't have one. Now I'm going to use a big propane burner, so I'll get this hot and just put it in there and just keep it hot for about 5 to 10 minutes. Okay, that was about 10 minutes. This is in a draft-free environment, so I'm not worried about it cooling down on one side of the stock, and the radiant heat from those fire bricks will keep that warm for quite a while. So I'm just going to leave that now and let it cool down to room temperature, and then we can do the last operation, which is bringing the diameter of the piston to the correct size. That's what the piston looks like after the heat treatment process. So it's got this charcoal grey oxide on all of the surfaces, but what we need to do now is machine this outer surface here to bring it to the correct dimension to fit the cylinder. Now, full disclosure, I've already done it on the other piston. So this was the first one that I did, and I used this one to dial in the correct dimension. Now I've got that dimension written on my top slide. I've got it set in the DRO. So I can go ahead now and machine the other piston and hopefully hit that same dimension. Now I'm not sure what I was worried about with this one. I've checked it all over and I think it would be fine. But it has given me that opportunity to try out some of the machining operations. Now in order to drive the piston, I've got a little stub arbor sitting in the 3-jaw chuck here. This has been machined in place, and that diameter is the same as the counterbore in the bottom of the piston. So I can slide that over. And in order to drive that, I've made a nose to go on one of my live centers. So it's just a press fit on the end of the live center, and that will fit without hitting the baffle. And it just puts sufficient pressure on that to make it cut. Now to do the cutting, I'm going to use my diamond tool holder, and I'm going to machine from the headstock end toward the top of the piston. And doing it that way, you get a sort of a shear cut, and it leaves a better finish with these very light cuts. And I'm going to check it with a micrometer when we get really close, but hopefully we'll get 2 pistons that are good fits, and yeah, got a spare. We're at 23.97 and we're looking for 23.95, so really close. Yeah, 23.95. Although that digital micrometer I got is great, it's very bulky and I just find it's really hard to get a good feel on the part. It's sort of heavy and bulky and difficult to see around. I think the old school Mitutoyo is probably better for me. Alright, now this probably should just go in and it starts to get tight about there. So that's to be expected. The bore in the cylinder is very slightly tapered toward the top, so it would get tighter as it goes up inside the bore. But what we'll do now is we're just going to polish this with some 400 wet and dry just to tune that fit. So I've just got a strip of 400 wet and dry wrapped around the steel rule. There you can make a fancy lap. Alright, that's going in probably about 75% of the way. So I'm going to leave that there. I can fine tune this later. As long as that's fitting in there, I think we're good. Let me do a partial assembly and I'll meet you over at the bench and we'll just see how good it really is, whether it pops when we take the piston out. Okay, I think I need to wind up here, and I was really hoping to get all of this assembled and show you the engine cranking over just to demonstrate that we had compression, but it turns out there's a problem. Now, I know how to fix it, but I haven't got time in today's video to do that, and I'll show you what the problem is, but we'll fix it next time. But what I did do was I went ahead and made the gudgeon pin, and it's just a piece of 1/4" drill rod or silver steel. Whatever you have that's precision ground and accurately finished on the surface, that would be fine. And it's been drilled through 5/32 and countersunk on the ends of that bore. Now the caps that fit in there are just made of aluminium. Now in the original drawings for the Titan engine, these were described as being aluminium aircraft rivets, and I guess if you had some you could use those. I machined these up on the lathe and I just finished them in a collet, gripping it by the 5/32 shank there, and the ends of the head were rounded over. And the idea is that when it fits through the piston, it should be just clear of the diameter of the piston. So those little aluminium caps there, if they rub on the cylinder wall, they won't score the cylinder wall, and it just sort of floats in between the two sides of the cylinder bore. Alright, let me assemble this to this point and I'll show you what the problem is. It was something unexpected and I was scratching my head when it wouldn't turn over, but I can hopefully show you inside the back of the crankcase to see what's going on. Just before I do the full assembly, I thought you'd want to see this. So I've got the piston in the bore there now, and if I press that down past the exhaust port, I can feel the compression and I can feel the piston bouncing up and down inside the bore. And if I block off the exhaust stack, the port, and pull it out, and that sounds very promising. So I think once it's just run a little bit, it'll free up really nicely and we'll get that nice compression. But let me do the full assembly now and I'll try to demonstrate where the problem is. Well, there's the full assembly of the engine now, and I was hoping to show you this doing a full 360-degree revolution, and I had just finished up on a process which I haven't got time to show you today. I'll do it in the next video. But what you have to do is cut a little bit of clearance in the side of the crankcase to allow the connecting rod to do its full 360-degree rotation. Now all of that's shown in the drawings. It's also mentioned in the build notes, but I just didn't have time to show you today. But I got the engine assembled and I thought now I can flick this over and see what happens, and imagine my disappointment when you get to this point here and it just stops. And you can hear a hard metallic click, and when you go the other way you get the same thing on the other side. It just doesn't want to go. Now I was totally mystified because I'd done exactly what it said in the drawings, and it should have allowed the connecting rod to do its full 360-degree rotation. And I ended up getting a torch and having a really close look, and what I found out is the connecting rod is actually making contact with the skirt at the bottom of the cylinder, not the crankcase. So I'll see if I can show you. So I don't know, is the camera going to see that? But you may be able to see the skirt on the bottom of the cylinder just hanging down inside that bore, and that's what's making contact with the connecting rod. Now it's a surprise because it doesn't mention it anywhere in the build notes. It's not shown in the original drawings. It was in the magazine article, and I know how to fix it. I'm going to have to go back to my CAD model and model in some clearance on the bottom of the cylinder. Be a fairly straightforward fix, but I've got to do it properly and I need to make sure it's correct in the CAD model. So I'm going to do that next time, and I'll also demonstrate the method for cutting the clearance for the connecting rod in the crankcase itself. Now I think that's all I've got time for today. I have got some wildlife clips to show you, and when we come back next time I'll show you how I've resolved that issue with the connecting rod and the clearance. And we'll also move on and start work on the back cover for the engine. So please join me for that. And just before I go, there are 3 people I've been in contact recently who are all building one of these engines or starting to build, and they've been sharing pictures and information with me, and we just comment backwards and forwards about some of the problems of building the engine. But 2 of them are shown here. Now this one that you can see on the screen at the moment has the cylinder finished in black Cerakote. Now Cerakote is a very special commercial product used in a similar way to powder coating. So it's usually sprayed on and is cured at high temperature. But Cerakote is got a beautiful finish, and it's able to withstand the sort of temperatures that we're likely to find in this engine. So yeah, it looks great. The other one has been finished in a high temperature black paint, similar to the sort of thing you'd put on exhaust manifolds in cars and so on. And both the builders have finished the cylinder heads and done a fantastic job. And it's just nice to be able to be in contact with people who are doing the same job that I'm doing here. So yeah, keep up the good work with that, and come back next time, and we'll move on with the build. And shouldn't be long now before we can get this thing popping and then we'll decide whether it's actually going to run. Okay, espresso. Thanks for watching today. I'll see you next time. Cheers. There's a bit of argy-bargy going on between this currawong and a bunch of kookaburras. It's actually 2 currawongs. They're probably nesting and they don't want the kookaburras around. There's been lots of beak clicking. There it goes. To be honest, I don't think the kookaburras are really bothered. This is a king parrot feeding on the cordyline berries. A bit manky looking. So something's had to go at its head. You lost some feathers, mate.